This here is a top-down picture of the Tevatron at Fermilab in Illinois. This is one of the most powerful particle accelerators ever built. It accelerates protons to tremendously high energies. Energies so high that if we just used kinetic energy equals 1/2 mv squared, we would find that the velocity is much, much greater than the speed of light. And yet, if we actually measure the speed of those particles, we find that while the speed gets closer and closer to the speed of light, it is always less than the speed of light. So in this chapter, we're going to try and understand how that happens. This is a chapter on relativity. We're going to focus on what's known as the special theory of relativity, meaning we're going to ignore gravity and, for the most part, not worry about accelerations. Now, we've already had some experience with relativity in Physics 101. We understood that we could look at things from different viewpoints. For example, you've probably had the experience where you've been sitting in a car and looked out the window and saw a car moving forward and felt like you were the one drifting backwards. It's difficult to know which car is moving, as long as they move in a nice, smooth fashion. We learned that velocities change in a simple fashion, and that positions change in a simple fashion. But accelerations and Newton's laws still hold anytime we move from one reference frame to another that's moving at a constant speed relative to it. This is the idea of what's known as Galilean transformations. The position, or the change in position in one frame of reference, or in a new frame of reference, is equal to the change in position in the old frame of reference minus how far the new frame of reference has moved compared to the old frame of reference. So that's the relative velocity times the change in time. And the assumption in a Galilean transformation is that changes in time are the same in all reference frames. This is actually what's going to break down here in special relativity. This sense that the time is the same for all reference frames gives us a very tightly ingrained notion of space and time. Specifically, if I were to plot time on a y-axis like this, and space on an x-axis, just call it x, but know that it represents all three space dimensions, then our natural ingrained sense is that everything happening at the time right now, this is now, and it's also here, our single point in time. Everything happening then is known as the present. Everything happening later is known as the future, and everything happening before is known as the past. We're going to find that this simple breakdown of space and time doesn't work so well. In fact, this separation of time as being invariant when we change from one frame to another doesn't work well.